Today in this video we will discuss about the expression for potential energy due to a spring. For potential energy stored in a spring. Okay. So we will discuss about potential energy stored in a spring. So we can see that first of all we discuss here a spring we are considering. A spring whose one end is fixed. Okay, the rigid support is there, from that one end is connected and another end is connected to a mass. Okay, and it is allowed, this mass is allowed to move on a very smooth surface. This mass is moving on a smooth surface if you are stretching it and releasing. Okay, so we can say that this is the equilibrium position. Equilibrium position. So once you stretch, for example, if it reaches up to here, and you are stretching, okay. In next case you can go like this. So from this position it is stretched and it reaches up to here. Okay, this entire spring is stretched. Again, what happens if you are stretching and releasing? So what happens? It will come back to its mean position. Again, it will go to here. Again, it will come back and that oscillations will be continuing. So here, whenever you are stretching or whenever you are compressing and releasing, what happens is that there will be a restoring force which tries the spring or tries the object to bring it back to its equilibrium position. Okay, which tries the object for which that restoring force will be developed in the spring which tries to bring it back to its equilibrium position. Okay, so if you are stretching, what happens? The restoring force should be developed opposite to the direction. So we can say that restoring force will be acting, which will be opposite to the direction of displacement. Okay. So according to Hooke's law, we can write, according to Hooke's law, the restoring force that we call it as spring force, Fs, spring force, that acts, that is proportional to displacement. If it is displaced more restoring force is needed to bring it back to its equilibrium position, and if it is displaced less, either it is compressed or released. Okay, not a matter. From the equilibrium position, if it is moved, less restoring force is needed to bring it back to its equilibrium position. Okay, so we can say that this restoring force is directly proportional to displacement and it acts in the direction, or it acts in a direction opposite to the direction of displacement. So that is given by Hooke's law. It was the experimental observation of Hooke, and from that he arrived at the law of Hooke's law. That is the spring force, the restoring force act on a spring when we are stretching or releasing. A restoring force will be developed which will try to bring it back to its equilibrium position, and that restoring force is directly proportional to displacement. If more displacement is there, more restoring force is needed to bring it back to its equilibrium position. Similarly, restoring force will be acting in a direction opposite to the direction of displacement. So this from the experimental observation. So we can write restoring force is equal to minus k into x, and this k constant is known as, here k is a constant and that constant is known as spring constant. The constant is known as spring constant. Okay, and the value of spring constant will be small. K will be small if and the value of K is large if it is rigid. Okay. You can say it is a spring soft and K value will be large. You can say spring is rigid or stiff. So by knowing the value of K, we can say whether the spring is soft or hard. But for a given material, we can say that spring constant will remain constant. Okay. And you can see or you can find the unit and dimension from this. What will be the unit? Unit of K is equal to, even though it is a constant, it is not dimensionless constant. It has unit and it has dimension. So you can find from this Fs by x. We are not bothered about negative sign because that negative sign will not contribute anything for the unit. Negative sign only indicates that the restoring force is acting in a direction opposite to the direction of displacement. Okay. So what you will get? What is the unit? So you can write unit of Fs and unit of x. And what is the unit of Fs? Newton and x. So Newton per meter is the unit of K. And what's the dimension? Dimension of K is equal to dimension of Fs by dimension of x. Fs has a dimension m L t raised to minus 2 divided by L. What you will get? We get it as m t raised to minus 2. Okay. So this is the expression for the unit and dimension of spring constant. Okay. Is it clear? And now we can check whether this spring force is a conservative force or not. Okay. Work done by spring force. Work done by spring force. Okay. So we know that the spring force is given by minus K dx. Minus Kx. So if it is displaced by small amount of dx, we can write the small amount of burden can be written as Fs into x. Actually Fs dot x. So you can write it as minus Kx into dx. In small amount of burden, we can write it as minus Kx dx. Okay. So small amount of burden by the spring force. When that object is displaced, when the or that object connected to that spring, if it is displaced by dx, a small amount of burden is given by minus Kx dx. So the total burden can be written as, if initial position, if we are taking it as xi, here which is the variable? X is the variable. So we have to give the limits of x. So if initial position is xi and final position is xf, so the total burden, here also actually you have to integrate from 0 to w, total burden. So we can write it as minus Kx. Or we can write total, if you integrate dw, you will get w, and if you apply the limits, you will get the total burden w is equal to minus k into integral xi to xf x dx. So if you integrate x, what you will get? What is the formula? Integral, already you know. You can write here. Integral x raised to n dx is equal to x raised to n plus 1 by n plus 1 plus the constant of integration. Here since we are applying the limits, no need of worrying about the constant of integration. So what you will get? Integral x raised to 1 dx. So you can write x raised to 1 plus 1 by 1 plus 1 between the limits. What is the initial value? Xi and final value x. Okay. So the total work done by the spring force can be written as minus k into x square by 2. X raised to 1 plus 1 by 1 plus 1, you will get it as 2. So x square by 2 between the limit x I to xf, or you will get the button as minus k by 2 into xf square minus xi square, or minus sign if you take inside, but you will get k by 2 half k into xi square minus. So this is the expression for the work done by spring force. Okay. So you can see that this work done by spring force, it depends only on the initial and final positions, because it depends on k, but that is constant for a given space. So we can say clearly that it depends only on the initial and final position. And if we are finding work done for a closed path, what you will get? Work done for a closed path. Closed path means starting from SI, initial position is XI, final position is also XI. So what you will get? Work done is equal to k by 2 into xi square minus xi square is equal to 0. Okay. So by these we can conclude that spring force is a conservative force. Okay. So we can conclude that work done by spring force does not depend on the path taken, it depends only on the initial and final positions, and work done for a closed path is equal to 0. So remaining observations also we can prove. So we can say that the spring force is a conservative force. Okay, is it clear? Spring force is a conservative force because work done depends only on the initial and final positions, and work done for a closed path is 0. Okay, these are the properties of conservative force. So we can conclude that spring force is a conservative force. Now we will discuss how to find an expression for the potential energy stored in the spring. Okay, potential energy stored in the spring. So already we discussed this. Potential energy can be stored either elastic potential energy is there, gravitational potential energy is there, electrostatic potential energy is there. So gravitational potential energy already we discussed, and here we are going to discuss elastic potential energy, that is potential energy stored in a spring due to its configuration. Okay, clear? So here we already discussed the expression for spring force is given by minus kx. So if we are plotting a graph between x and the spring force, we can say that graph will be like this. Fs equal to minus kx. Here we can write this will be equal to minus kx. So when we are plotting a graph between Fs and x, the graph will be a straight line like this. Okay, and now we can find the work done. How? If it is having a maximum displacement of xi, okay, corresponding to xi. Initially it is at the equilibrium position. Equilibrium position corresponds to x equal to 0, and it is displaced up to xi. So we can find the work done. How to find the work done? If we know the graph, or already we discussed, we can find the work done if a graph is plotted between force and displacement by finding the. So we can write work done is equal to work done by spring force is equal to area of triangle. Okay, and that can be found out half into AB into half into AB into OA, or half into AB is equal to the force acting, so that is equal to minus kx, half into minus kx. Here x, instead of x we can write xm, the maximum displacement, or we will get it as minus half kxm. This is the work done by spring force. Okay. Then we can find what is the work done by applied force. Work done by applied force is equal to, at least we have to accept that applied force should be having magnitude equal to plus kx. So we can find work done by applied force is equal to minus of work done by so we can write it as this is equal to half kxm square. So this work done will be stored as the potential energy. Okay, so we can write potential energy of the spring is equal to half kxm square. Okay, the potential energy of the spring can be written as half kxm square. What is k? K is spring constant, xm is the maximum displacement, that is it is displaced from 0 to xm. Like that we are using. Otherwise what we will get? We will get xf square minus xi square. Half k into xf square minus xi square, like that we will get. Okay, is it clear? So this is the expression for the potential energy stored in the spring. So we can say that potential energy stored in the spring will be equal to work done by the applied force, which is equal to minus of work done by the spring force. Okay, is it clear? Mechanical energy. Mechanical energy in the case of a spring. So already we know that the spring force is a conservative force. So total mechanical energy should remain constant, conserved. So if we are considering the case, spring is there. Connected to an object. So this is the equilibrium position, and it is and it is, we can write equilibrium position. When it comes to here, we can say that it is the extreme position. Extreme position. And here also when it is compressed also it will reach, no? This we can say this is maximum compression, that position we can say another extreme position. Maximum compression and maximum elongation. Okay. So when it is at the maximum compression and at the maximum elongation, we can say that, but we can say the potential energy will be maximum. This is xm, and this also corresponds to minus xm, okay, and here x is equal to 0. So when it is at the extreme positions, we can say total mechanical energy will be purely potential. Okay, so we can write at extreme positions total mechanical energy is equal to purely potential energy, and that it is given by half k xm square, because at that instant that object will be. And when it comes to mean position or equilibrium position, what happens? At equilibrium position, total mechanical energy will be purely kinetic. That is equal to purely kinetic energy, and that is given by this purely kinetic energy, and that is given by half m maximum velocity it will be having mass of the spring can be neglected in comparison with this mass. Okay, negligible mass is there for the spring that can be ignored if we are considering the mass of the. Okay, so at equilibrium position, when it comes to equilibrium position, because what happens that time, what is the value of xm? Xm is equal to, what is the value of x? X is equal to 0 when it comes to equilibrium position. So potential energy will be 0 and kinetic energy will be maximum. So here you can write, and kinetic energy is equal to 0, and here you can write potential energy is equal to 0. So in between these two, in between them means in between extreme position and equilibrium position, total mechanical energy can be written as, it will have both kinetic energy and potential energy, and that is equal to half kx square plus half m. Okay, half kx square plus half m v square. Okay, so we can find what is the maximum velocity if we know the maximum displacement. How to find? Total mechanical energy is concerned. So we can write mechanical energy remains constant because conservative forces, spring force is a conservative force. Since conservative force is acting, total mechanical energy remains constant. So we can write half kxm square is equal to half m Vmax square. What is Vmax? Vmax is the velocity of that object when it comes to equilibrium position. Okay. After stretching or after compressing, once it is released, when it comes to equilibrium position, that velocity is known as Vmax. Okay. So you can find the velocity Vmax is equal to half m. We can see what you get root of. So maximum velocity can be written as root of k by m into xm. Root of k by m into xm. K is spring constant, m is mass, and xm is the maximum displacement. Okay. Or sometimes they will give what? This will be given by velocity. Maximum velocity will be given. They may ask to find the maximum or what is the extreme position. So vice versa you can find it. Okay. And when it comes in between any position, what is the velocity? How to find? Velocity at any intermediate position. Velocity at any intermediate position. Intermediate position means velocity at any intermediate position means between extreme position and equilibrium position. In between these two, it will have both kinetic energy and potential energy. So again we can write half kx square plus half m v square is equal to. Here also total mechanical energy should remain same. We can write half kxm square. Half mv square is equal to half k xm square minus x square, or half can be cancelled. V is equal to root of k by m into xm square minus x. So this is the expression for the velocity at any intermediate position. So if, for example, if it is given a spring is having spring constant some value, mass of the object is given, maximum extreme position is 5 centimeter. So what is the velocity of the object when it comes to 3 centimeter or 2 centimeter? So all data is given, you can substitute by using this formula. Okay, is it clear? So we can say that whatever may be the case, the total mechanical energy remains constant. So when it comes to equilibrium position, total mechanical energy is purely kinetic. When it comes to the extreme position, whether it is maximum stretch or maximum compressed, total mechanical